Good afternoon. We're going to talk about JSR 385, the Java Units of Measurement Standard version 2, and how it could have saved NASA and also many other victims of unit conversion or other numeric mishaps, a lot of pain and money.
Yeah, so I would say hello from my side as well. Let's meet. Doris Weiss from the Java user group, founder and leader. I also work for ABN AMRO as a Scrum Master, and also I do run a small company on my own where I'm trying to motivate others do crazy things that they want. But today, as Werner mentioned, we're here to talk about JSR 385. So Werner, who are you?
Yeah, I'm Werner Keil. I'm one of the spec leads, or now it's actually maintenance lead because the JSR has finished. I'm also the maintenance lead of the managed JSR, so those of you who are here for the whole week or more than one day, I have another talk with co-maintenance lead Anatol Klesch tomorrow about the managed JSR, and those who are interested in more than just this particular JSR, you're more than welcome to also come by tomorrow. I'm also an agile coach, software architect, and Java consultant in various fields, anything from embedded to large enterprise systems. Right now I help the German insurance system and e-health network to add a little bit of security also based on Java.
So what are we going to talk about?
So the Mars Climate Orbiter launched on the 11th of December 1998. That was the same year that I went to Java 1 for the first time, by the way, even though it's not called Java 1 anymore. Here are a few stats. The whole mission cost $125 million. Some approximations are even higher, especially with the bad PR. And it was supposed to study the Martian climate and atmosphere and changes in the surface. So climate change on Mars if you want. Here was the problem as it was explained by a NASA engineer. Basically, different contractors and different departments used different unit systems. Some of them used the metric systems, while others used the customer system, and then the numbers were translated between those parts without being aware of the unit, so that caused a miscalculation in the other system because it thought that something that would have come as inches or miles per hour were actually kilometers per second or vice versa. There are also a few other similar cases. The most important one is that America would not have been discovered without a miscalculation. Columbus thought he would go to India. The Gimli glider, an Air Canada plane that ran out of fuel after Canada had switched to the metric system. Oh, that's actually the same. The picture is Clarence, the tortoise. In 2001, it was lent by one, actually American zoo in the US to another one. And over the phone, they only briefly mentioned the weight of the tortoise. And one person on the phone assumed that it would be pound, but it was actually kilograms or vice versa. And so they built the fence in a much less appropriate way, and the tortoise just ran against it and dragged it. Yeah, I guess probably similar to what you see at the Mexican border right now, where the unclimbable fence is actually not so unclimbable. And a whole set of medication errors. Unfortunately, some of them even ended up lethal when a patient received the wrong dose of a particular medication. So what's the fundamental problem? First of all, Java primitives are, as the name says, primitive. So they're meant to be building blocks for other more complex types. For example, you would have a double. Here it would actually be more descriptive to tell what it is, but it would only be based on the name of the variable that you can guess or know what it's supposed to be. Here the same, for example, in a particular unit system. And that's how it could be, or actually can be, if you use JSR 385 or its immediate predecessors like JSR 363.
So yeah, actually, you know what? What Werner showed creates an equation. Of course, it could be really easy to start creating or developing your own library, right? But then there are a few issues coming up, at least to my mind, right? So, of course, there is development you need to take care of, maintenance, and what else? Upgrades and other extensions. So here comes my question. Do you really believe you're a domain expert and you know the SI system that well so that you are able indeed to create your own library, maintain it, upgrade it, and perform any other kinds of extensions? Well, let's see why we do think this is a no-go, at least. And of course, we do have our own JSR, but I will park this for now. And step by step, we will show why JSR 385 is there for you. So, Werner, what is JSR 385?
It's an upgrade or an evolution to the first version that launched 3 years ago, approximately the same time, under the name 363. It focused, first of all, on the redefinition of the SI system. How many of you have heard about those changes that are actually in place right now? Okay. Well, in everyday life, it usually doesn't affect you that much. But when you do calculations here and there are certain formulas that have to be adjusted. And of course, there's also a lot of documentation that has to be adjusted. And we launched some modules on top of the reference implementation that are dedicated to, for example, the SI system or other systems that build on top of that as well. So that was the original goal of the JSR. The basic concepts are around certain elements like dimension, unit, quantity, or prefixes. That's actually something that we added in the new version, that the prefix is standardized, and we also provided the two major prefix systems, binary and metric, in the API, so you don't have to care about that even in implementation. And they can be used across different implementations. And unit converters. Plus there's some support for parsing data or representing it in the UI, for example, or in reports. And the concept of a unit system, which can then be implemented by either the SI system or others, that also includes, for example, the unified code for units of measure, which is an open, extended version of the ISO standard. But there are also others which we cannot make them available, especially ISO 80,000 is, for example, proprietary, and it's sold by ISO or DIN or other local subsidiaries as big books, but due to license terms, we are not allowed to make that available as open source. But for example, the UCUM catalog, which is very close to that, is made available open source and publicly to everyone. So that's why, for example, the Unified Code for Units of Measure is one of the implementations of a specialized and very extensive unit system.
So that's a cool one, and now I need to come closer to you, Werner, because we do have a little exercise at least. So what is the exercise gonna be about? Of course, we do have different personalities and body types. So let's talk about our body mass index, right? So we could have an exercise like write a program to calculate the BMI of a person. And of course, BMI is a person's weight in kilograms divided by his or her height in meters squared. So let me directly go to the demo itself. It's a very simple demo, and I will explain together. It's not visible there, so let me drag it. Yeah. Okay.
Is the font size okay, even in the cozy back rows? Yeah.
Yeah. But here comes the question. I cannot see it from here. I don't have a double screen, so I will come here. And let's talk a bit together about it. Of course,
there's a laser in there, by the way.
Sorry?
I think there's a laser in your...
Oh. Yeah?
Yeah.
So if I do
There's
this...
a laser pointer.
No, I mean, I don't have it on both screens.
Ah.
Anyway, I will stand here, actually. So, what do we see there? First of all, we will try to define the mass and the height. So, we will just define two quantities and we will print them out. As you can see, actually, it's really easy, as Werner showed a few slides earlier in the red font, to define a quantity. So what we do there, I got this. Yeah, cool. So what we do there is actually we define a final quantity of a type mass, and then this is something like 75 kilograms, right? Same way to define a height itself of a quantity, of course, of length. And then this is the printout. But not the right printout, so let me run it once again, if I get it. Yes, it should be, it's a bit difficult. Yeah. If the people from the committee here can help us to do this thing. No, I mean, I don't have it, I don't have the double screen, yeah, unfortunately. But let me try do it this way, actually. So, if we go, it will be a bit tricky to go with the rest of the demos that way. But yeah, this is the very easy way to go. And at least, yeah, that's it actually. So let me go directly back to the presentation itself. So that was a very simple way to actually define two quantities and print them out. Of course, there was something missing, right? And what was actually missing, or maybe you already had it in mind as a question, how do we really set up a project to be able to use these crazy units of measurement API, right? So the only thing you need to do if you really want to use JSR 385 in a project of yours is to do this thing in your POM XML file, right? So actually you just need to include the Intriga dependency in your POM file. And we recently finalized, or we went final with the 2.0 version. So you can even use that one. It's the very latest one.
Actually, it's 2.1. But they're functionally the same, but a few improvements were done primarily for the Java module system. So if you want to use Jigsaw, 201 has a few improvements that side.
Yes. So that was a very basic demo to begin with, actually. And now, Werner, what about the quantities themselves?
Yeah. So a physical quantity, as per Wikipedia, is a property or phenomenon of a body of substance that can be quantified by measurement. Yeah, that's way scientific. Here's another explanation that's probably even more technical, especially when it comes to the real number. Let's look at an example. Here we have the speed of light that has a numeric value and a unit which is meter per second. So the same physical quantity can also be represented equivalent in several unit systems. That's why we extended the simple equals method also in the latest version by additional methods that are called equivalent, simply because the Java type system is very strict. In Java, if you have a big decimal 1, a big integer 1, and an integer 1, even though they are all the same value 1, Java will tell you, no, they are not equal, because the type of the class is different. And that's why here we actually have a combination of several types underneath the hood, and they all need to make sense. So that's why we added this notion of equivalence, where, for example, you could also compare 100 centimeters and 1 meter, and they would be equivalent even though they are not equal. So here's an example of converting meters to second into kilometers per hour. Okay, another exercise?
And yes, more or less I explained that on a bit earlier as well. So the next one is about defining the mass itself by the square of the height and print out the result. I will go through it very quickly, also looking at the time we spent and the technical difficulties we are facing. But we do have some more demos in the very end as well. So, as far as I can see at least. So what do we have here? We define, of course, a mass in the very beginning, and then a length. For the length, of course, we do need to take the meter constant from the units in numeration. Then we print out both, and yes, this is the right. I will also explain a bit the quantity itself. As you see, what do we do here? We define a type agnostic quantity for the BMI itself. So first of all, or actually we will do it with two ways. So first of all, we will divide the mass twice by the height. So this is the one way to do it, just to show you that it works in both ways. And of course, the second way is we will divide the mass by the result of the multiplication of height times height. And of course, if I will run this one, I should get two printouts. Of course, with a slight difference, because there are a few peculiarities of the system itself. But of course, it doesn't really matter. We're talking about 2 zeros. As you can see, also from the previous example, we did get the units right, or in the right printout, and of course the result in the good format as well. So let me go back to the presentation. I will skip those ones. very quickly also looking at the time and the things we have to say. And Werner, what about the units themselves?
Well, the base units, which are defined by the metric system, here actually also the new layout that came with the redefinition, are the ones you see here. And then there are derived units that can be based on those base units, for example, kilometers per hour, as we already saw in the example, and several others. There are also submultiples, for example, kilometer, millisecond, megameter. Well, technically it exists, although it may not be so common, but in the extended unit systems that sit on top of the SI system, we also have, for example, Indian numbering systems where you can define crore or lakh meters. And even without money, we'll come to that tomorrow in our talk, but even outside the monetary context in countries like India or I think even Pakistan, they are not so different when it comes to numbers. They may be different when it comes to politics, but in those countries, crore and lakh are pretty common and also used in everyday life. So you may not see it on a street sign, but you probably see people talking about, oh, this city and that city, there are so and so many crore meters or kilometers apart from each other. Kilosecond is also a little less common.
Yeah, we'll skip those ones, given that we are running out of time, I would say. So, what about the dimensions themselves?
The base dimensions pretty much go along with the base units. So we have length, time, mass, electrical current, thermodynamic temperature, amount of substance, or luminous intensity. And one is basically a special dimension. It's a dimensionless dimension that can be used for units that don't have a dimension. So here, for example, force.
However, yeah, indeed, I mentioned the majority of our examples will be shared after this presentation, and it is just a very simple GitHub repository, but I do think at least this one we should show. So, auto-detect which argument is the mass and which one is the length. So, again, please be patient with me. What do we have here? Of course, we pass everything from the command line, and we define initially both of the quantities to be null, actually. And then, by a get unit method, and of course, the sub method of a get dimension, we try to figure out which argument corresponds to which particular dimension. And of course, with a simple if-else, this is how we can do it, actually. Right? The important part here, I would say, is that we can define things as per type. And if I'm not mistaken, I can also show you something different, because when I'm talking about the S-type method, this example is also interesting, I would say. So, we are still in the same example. We are still talking about the body mass index, right? So we are still talking about weight and height. So what are we doing here? We did define a custom interface, right? Which personally I find it good or cool. Which of course extends the BMI. This is a bit of tricky to keep it in mind, but the way we can go to achieve what we want is, of course, the very first lines are via our normal command line arguments to get the quantities the way we would like to parse them. And of course, here, what do? We define that this new quantity will actually be of a type of BMI, right? Which is an interface we just defined here. And same applies to the unit itself. Now, as I said, we do have quite a few things to show. So, let me just do a quick, or show a quick summary table. And Werner, is there anything we're missing from here?
No, I'd say all the base quantities and base units are there.
Okay, so I guess now it's time to go to the interesting part, right? And for the ones you didn't notice it yet, I came today morning from the Netherlands. So I do have with me stroopwafels. And guess what? Later on, we'll play a quiz. So for the winners of the quiz, there will be some stroopwafels. But for now, of course, talking about the maths themselves, let me start directly with equality and equivalence, because Werner already mentioned about some equivalences we defined in this library. So let me actually start with the units themselves. And I will try to go a bit fast here, but if you feel like it's too fast, just raise your hand and stop me. But I believe it's quite straightforward. So regarding units, what do we have? A kilo is always different to a millihertz. These are the assumptions we had to define actually in the library. A kilo and a million are always different, of course. Kilo and a kilo are equal. A newton and a kilogram times meter per square second, they are equivalent. Here comes the cool part, though, I would say. Kilogram per square meter is equivalent to milligram per square millimeter, right? So, yeah, it's a bit tricky. So again, here comes my question. Should you actually use functions to normalize the expression into what could be closer to the base unit? I would say this is something you could consider, and the same applies also to quantities. If you say the equivalent one, I will explain all of them actually, but if you say the equivalent one here to what I just mentioned, what do we have? Here we have 1 kilogram per square meter is equivalent to 1 milligram per square millimeter. So which one should we actually use? Of course, normally we should make a conversion on the base unit actually, right? But there are a few cases where you might indeed need to use something like that. For example, for a very special paint for small devices, you need precision, right? So you might need to use this one, the milligram per square millimeter. And of course, as I mentioned, I did miss a few items here. So quite straightforward, I would say. 1 kilo is different to 1 millihertz. 1 kilo is different to 1 milliohm. 1 kilo is equal to 1 kilo. And 1 newton is equivalent to 1 kilogram meters per square second. Yeah, I would like to go directly to the next slide, but I still have something to show here, which is this one. So, what do we see here? We see on the left side a quantity of kilo, or a prefix of kilo, and on the right side we see ohms. So, of course, 1 kilo equals 1000 ohms. So the question is actually that it's not only about converting the values, it's not a question actually. It's not only about converting, as you can see, the values and the units, but it's also about doing the comparison and converting to one unit and making use of that one reference unit in order to be able to achieve what you want regarding all the equations that you have. So that's it from here, and let's talk a bit about quantity addition, right? So of course, as we know from school, and this is not a quiz actually for the Stroop-Wafels, not yet at least, 1 ohm plus 1 ohm equals 2 ohms. What do we have here? 1 ohm plus 1 milliohm. Yeah, what is this, right? Okay, let's see the next one. Maybe it might make more sense. So 1 million plus 1 ohm equals, why? Why is that? Because there are, as I mentioned, of course, in the very beginning, I mentioned that the SI system has quite a few peculiarities which you need to take care of if you're about to write your own library. However, still, in order to find a good workaround and a good use case for such scenarios, what we had to do actually is the following assumption. So we basically say that for such equations, we will use the first unit if we can, right? So if we can use ohm, let's do it. However, if it leads to an overflow, we need to fall back to the second unit, right? And of course, there is one more case when both units lead to an overflow, then we just throw an overflow error. So for example, this one, of course, you see it does not compute, but the technical exception you will get is the incommensurable exception, where you are prompted or you are being informed from the system that you're not able to actually do such a comparison.
Okay, the last one, the compiler would not even allow you to do.
Yeah. So, yeah, I talked about quiz, right? I already gave you a hint. So, what is this? Yeah, we're gonna have a quiz. And what is the quiz about? Is it visible also to the very back seats? Yeah? Okay, cool, thank you. So, how much is 0 degrees Celsius plus 0 degrees Celsius? I would be, yeah, that's quite straightforward, right? Yeah, I see someone laughing there. However, if I would be sitting to the very back of this room, I would be like, hey, wait, why is this dude that couldn't even create a double screen to show the demo asking us on a Wednesday afternoon such a question? Is there maybe something crazy behind it? So, yeah, let's see, right? Let's see together. So, of course, it could be 0 degrees Celsius, right? But it could also be 0 degrees Celsius. Or could it be 273.15 degrees Celsius? Who thinks it's 0 degrees Celsius? And I still need to say, I do have Stroop-Wafels with me. Okay, cool. Who thinks, and now I need to raise my right hand, who thinks it's the second 0 degrees Celsius? Nobody. Oh, okay, we do have one. Cool. And who thinks it is 273.15 degrees Celsius? Okay. So, the majority goes for the first 0 degrees Celsius, and then we have 273.15 and only one with the second 0 degrees Celsius. However, can you see the blink? All the three are correct, actually. And why? Why? Yeah, that's a good why. Does anybody know why? Yeah, shoot it. To the back.
It depends on the reference.
Sorry?
Depends on the reference.
Exactly. So, what happens actually? There is a distinction we always need to keep in mind. So the question should be, are we talking about an absolute? Or an absolute temperature or a temperature change? And that's why we have three correct answers here. So let's try together to go one by one through them. So for the first one, 0 degrees Celsius, what happens? Of course, let's take the scenario where both temperatures are absolute. So when we are talking about an absolute temperature, 0 degrees Celsius, of course, means 273.15 Kelvin. So what do we have? We have a sum of 546.30 Kelvin, which of course equals to 273.15 degrees Celsius. Does it make sense? I think it does. If not, let's go together to the second one. So, for the second one, what do we have? Of course, we already covered the scenario where we have two absolute temperatures. And now let's talk about an absolute temperature and the temperature change. As I mentioned, an absolute temperature for when it comes to 0 degrees Celsius, an absolute temperature means 273.15 Kelvin. However, when we are talking about a temperature change, 0 degrees Celsius means, of course, 0 Kelvin. So what do we have here? We do have something like that, right? Which makes a sum of 273.15 Kelvin, which, of course, is nothing else other than 0 degrees Celsius. Okay, so we talked about the scenario where we have two absolute temperatures. We talked about the scenario where we have one absolute temperature and one temperature change. So what's left? A scenario where we have two temperature changes. And as I already mentioned, when we are talking about temperature change, 0 degrees Celsius equals to 0 Kelvin. So we'll have a sum like that, which means, of course, 0 degrees Celsius. Yeah. So, what is here? All three answers were correct. And what, yeah. That's a good question. But we are talking about a temperature change, right? Yeah. Okay. Cool. So now that yes. You mean so you mean actually in our library, right? We do have.
Quantity has a so-called scale, as we have only 4.5 minutes left. I'm not sure how many of the demos we can show, but there's one demo about thermodynamic calculation and heat efficiency, where the delta T in Kelvin is also modeled that way. So there it uses the scale relative.
Let's have a discussion after that as well. So let me go quickly through the rest of them. Multiplication, first of all, okay, let me do a recap. All the three were right because, of course, of what we mentioned. And degrees Celsius is not a good unit to use. I will come back to that in the 3.5 minutes that we have, actually. Yeah, so multiplication is quite straightforward, actually. You will see everything makes sense, but in the third example, you really need to think about your case, actually. And it always depends on the case where you're going to use it as, for example, gram times kilometer, or the other way around. It depends on the particular scenario itself. This one is quite straightforward, and same applies to here. When you have something like that, should you keep it as is, or should you use it as square meters? It depends on your case, I would say. And for quantities, it's quite straightforward as well. You just need to multiply the values and the units, but the only strange effect, or the only thing you should think about, is the way you're gonna represent the final unit, actually. So division, straightforward, I would say, with only one point to mention. That's quite crazy, right? When you have kilometers divided by meters, does that equal to 1 kilo? Think about it. Yeah, quantities are the same here when it comes to division. And powers themselves are quite straightforward for both units and quantities. As you can see, I need not explain anything special here. But what do I have? Okay, 2 minutes left. Let me try go really quickly. Kelvin to the second power is, of course, square Kelvin, right? But what is the result of degrees Celsius to the second power? Does that equal to Kelvin minus 273.15 to the second power? That's the reason I'm saying Celsius degrees is not a good unit to use, actually. And same applies, actually, to this example, meters times degrees Celsius. What is that, right? There are a few cases you might need to use this. For example, for an isolation material, you could say this material can hold up to 5 degrees Celsius per meter, but it's the only one I can think of. So degrees Celsius is not a good unit to use. Same applies to quantities, of course. Of course, degrees Celsius provides a good use case, or a good case when we want an easy scale between 0 and 100 degrees, but it has some peculiarities which you need to take care of. So, about parsing units and quantities, you see that you can have several different scenarios, and you can use actually whatever you want. So you can use thousand separator, decimal point, the slash, of course, the asterisk, and here you see two differences. The sub HTML element, and of course the -1 Unicode, and the rest are quite straightforward. You can even use the caret, and the very last one, of course, you can have different versions of systems of units. We do have the metric in Europe, imperial, they do have, yeah, of course, in other countries as well, but US is the one which is being used from United States, yeah. And the Roman units of measurement for the traditional ones. Demo time, unfortunately, not.
I think we're almost out of time.
Fundamental problem again. No, I'm sorry.
Can you switch over to the IDE so we can just show it very
Yes,
quickly?
yes, very quickly. Let me just show it. You want to show the car demo, right?
That was the car demo and the thermodynamic actually side by side. Yeah, the first one, heat requirement demo. First up.
This one?
Yeah. So here you see the relative being used in the delta T. That's the delta in Kelvin, and in this case it shows very well that with temperatures, even though it's a difference between 50 degrees Celsius and 70 degrees Celsius, the delta is actually in Kelvin. That's why here you have the relative scale explicitly defined. Okay, so that's not so exciting, we don't have to run it, I think. The second one, here it's a little bit tricky, especially in the end, where we faced that you cannot simply convert quantities sometimes. This would be an example of gram or kilogram per kilometer, which is the carbon footprint. And I think, can we run those quickly? One actually you see here, the Porsche Cayenne, the SUV. If you drive from Frankfurt to Düsseldorf, it produces 77 kilogram of carbon dioxide. And as opposed to a smaller vehicle, a Smart 4.2, on the same distance would only produce 29 kilograms of carbon dioxide. Okay, I think now we really used our time, and I'm not sure if there's any time for questions, but you're more than welcome to come to us outside the room. I don't think we can occupy it anymore.
Just a very last moment, I would say, for the ones who did raise their hand, please come to me afterwards for stroke waffles. They're really cool with caramel. What I still need to mention, please have a look at the JCP page and the JSR page. As I mentioned, we went final last 2 months ago, was it? Something like that. And why you should actually contribute to the JCP community. At least for me, it helped a lot. I mean, I already see Werner getting out his award, but I need to mention as well that I started by just fixing documentation, then I did a JUnit migration, and what else? Werner. I think the only thing I can mention that now I heard of the JSR hackathon, but the most important part of it is that I do believe the community itself is quite helpful. And from my side, I need to also thank Werner, because he's every day on top of it, of any upcoming issues. And by the way, he got the JCP award at the Star Spec Lead this year for this JSR.
We won it. We won, and we actually beat Brian Götz and the Open JDK team, which is actually quite an honor and quite impressive having won against them.
So again, there are 3 categories if you're interested in joining the JCP itself, depending on whether you are an individual, an open source organization, or a community as we are, and a company. You can find more on the JCP page, or just come to one of us and ask us about it. We ran out of time, but I will share the demos themselves and some good first issues for the ones interested, and for any other kinds of questions, we'll be here for the rest of the day. Thank you.